It is my pleasure to introduce our speaker today. Professor Roger Blandford is the Luke Blossom Professor in the School of Humanities and Sciences at Stanford University, as well as Professor at SLAC National Accelerator Laboratory at Stanford also. Roger is a theoretical astrophysicist whose research has had transformative impact across a broad range of astrophysics, including the formation and collimation of jets powered by spinning supermassive black holes, particle acceleration and shocks, gravitational wave astrophysics, particularly relating to the strong gravity environments of spinning and accreting black holes, and the reverberation mapping of the environments of AGN, just to name a few. Among his many honors, he was recently announced as the recipient of the 2020 Shaw Prize. So congratulations, Roger. Today, Professor Blandford will be talking about ergomagnetospheres, ejection disks, and electromagnetic jets. Without further ado, I now turn the controls over to Roger.
Okay, well, it's a great pleasure to participate in this series, and I'm very eager to share with you some ideas. I should say that this topic I'm going to talk about is very much a work in progress, which I think is in the spirit of these talks, and I'm eager to get feedback on it. So if you have questions at the end, rest assured I may have even more, and so that's why I'm keen to do it. I think the spirit in which I prepared this talk, as I think there's three ways of looking at it. One is it's a sort of series of hot air balloons, if you like, that I'm floating up, and one of the things that one knows about hot air balloons is they return to Earth eventually. And this is a picture, I think, taken from just up the road from the VLA, so it's kind of appropriate. Another way to think about it is as a form of heresy, and this is a modern depiction of the heresy. And the third is a sign of it creeping senescence, and you can take your pick at the end of this. I should say my views over the years have been heavily influenced by many people, including this list here, but not restricted to it. And I thank them all for their collaboration and criticism, and they should be blamed with none of what follows. So with that preamble, let me start with something that's familiar, I hope, is M87 and the wonderful EHT observation. I think it was the most downloaded image from the NSF of all time, and deserved it. It was a fantastic, as we all know, it was a fantastic technical accomplishment, and what it took to get all these, not just these different observatories, but the astronomers who work there to produce a coherent image was truly remarkable. And I think, you know, front and foremost in this must be the tremendous work that was done using ALMA, which anchored the whole observation. And so the NRAO folks and their European counterparts and so on, who worked on this project through ALMA, deserve our credit, because it's not only is a great thing for the public, it's also a great thing for science, and it has a lot of messages, and as I think we all know, it's the start, not the end of an investigation. So we're all eager to see more from this. Well, as I'm going to very much de-emphasize the observations in this talk, because for this audience, they're not necessary, I hope. But just this is about the only slide with any observations, and I'm afraid, which normally I would have many more. But just to remind you that M87 is a giant galaxy in the middle of the Virgo cluster, some 17 megaparsecs away. It was the first jet ever found in M87 over a century ago. We believe it's 15 to 20 degrees to the line of sight. It's the jet power. Well, I'll come back to this point, but if you take the sort of nominal value, it's 100 times the power that you see from an accretion disk, including this wonderful 1.3 millimeter image. The black hole mass is about 7 billion solar masses, and that was about the first estimate from the 1970s, and it's been pretty stable, and this corresponds to 4 microarcseconds, and you know all of this story. Most of you, I'm sure, know that the disk is spin, as measured using Hubble, is aligned with the jet, but you also all know that this is fabulously under luminous, and because it's only about 10 to the minus 7 of the Eddington limit for such a high black hole mass. Here's what the jet looks like on a range of scales. Again, this is all familiar to you. I'll just draw your attention to one aspect of these wonderful images, and that is the evidence that one's seeing from many of these sources that much of the emission at the base of the jet comes from a sort of surface layer. It comes from an edge-brightened image, and it looks like it's where the jet boundary is interacting perhaps through a boundary layer with its surroundings. I'll read briefly. I said it's 10 to the minus 7 to the Eddington limit, but presumably this black hole grew, and in the past it was extremely bright, probably brighter than Vega. Had your ancestors been around to watch it, and they probably weren't around to watch it, they would have seen something that was extremely optically bright. And I was reminded, we had some perhaps appropriate music at the start of this from an older musical tradition. I recalled from my memory an old Pink Floyd lyric, and so here you have it. I didn't know it was a binary black hole, but I'll take it on trust that it was. And so let's move that. But whoops, back there. So what I think we can all get out of this is that jets originate at black holes, at least very close to them. They're clearly being confined and collimated by something, and they interact with their environments through a boundary layer. So that was, and this is more or less the end of the observations you'll see, simply because I think you don't need me to explain them. Okay, so let me go on to physics. And black holes, which of course has had a lot of attention, not the least because of the Event Horizon Telescope. If we just look at them classically and not exercise the febrile imaginations of theoretical physicists looking in other ways, and just look at them in the way that they are manifest in astronomy, then they're essentially just characterized by spin and mass, and the relevant metric was discovered in 1963, the same year quasars were discovered by Roy Kerr, and it's pretty much at the same meeting. And then in a remarkably short space of time, the properties of the Kerr metric and its general relevance to what we're observing became clear. And here are just 3 more people who are justly famous for their contributions to understanding black holes, amongst many. And here's the Kerr metric. There's an angular velocity associated with a black hole, and it's often expressed in terms of the specific angular momentum per unit mass of the black hole, which is known as A. It's equivalent to a spin angular velocity. This is the formula for it, if you like, in terms of the angular velocity and the mass. And then, whoops, sorry, back there. Then one of the things that was understood, particularly by Roger Penrose, when a black hole spins, there is a fraction of its mass that is extractable, it's reducible if you like, and it's associated with the rotation, and it's up to 30% of the mass of the black hole. And that's there for the taking, and he devised some thought experiments to show how this could be done, and I'll explain in a short while perhaps a more astrophysically practical way for doing this. So here is my sort of summary, and this so black holes can power AGN. It really looks like that is happening. I don't think I have to make that case, but the case that I am going to emphasize here is that the actual powering comes from both rotation and accretion. In fact, you can make a sort of slightly silly story that all AGN are powered purely by rotation. I certainly don't believe that, and I don't think anybody else does. But in principle, it's possible. But in practice, this is not the way I think galactic nuclei behave. But there's plenty of energy there associated with a rapidly spinning black hole. So let's turn to accretion. I just want to do a little bit of theory here. and deal with the very most simple thin accretion disk that doesn't really describe terribly well what is actually observed. Assume it's steady, it's axisymmetric, it's slowly accreting, it's thin. And one of the things that we do know is that there's a little bit of magnetic field there, gets amplified on a dynamical timescale, giving us the magnetorotational instability, famously investigated by Steve Balbus and John Hawley and many others. And this is a source of inevitable viscosity or torque in the disk, which will drive a mass inflow. And this mass flow, if you associate with a speed v and just keep the very simplest assumptions and give a mass per unit radius mu, then mu v will clearly be constant. Likewise for angular momentum, we've got a torque transporting angular momentum outwards, and we have an inflow that's bringing it inwards, and the difference of those two should be constant unless they've got some means of removing it or adding that angular momentum. And if you're, as both terms go as r to the 1/2, you expect that far enough out in the disk, that constant's effectively 0. Associated with this torque must be an energy flow, and that arises again with two terms. One is the gas. If I use my cursor, I think perhaps see that there. You have a gas that's carrying binding energy inwards, but then the torque itself, because the disk is rotating, does work at a rate g omega, and that transports energy outwards. And the thing that one teaches in graduate classes or whatever is that this energy flow has a divergence, and far enough out in one of these very simple-minded disks, that divergence, if it's a thin disk, will be 3 times the relativistic binding energy. The books are balanced by what's going on at the inner radius. And if it can radiate, then you get this power that's produced for the gratification of observational astronomers from all sorts of accretion disks. So that's one of the possibilities, is that that it will radiate away this divergence, the energy flux. Another possibility that's been widely discussed is that the energy is trapped in the inflowing gas. It can either do this, in the case of the sources we're interested in, it basically just does it as a hot ion supported gas, and the disk will thicken, and this is, if you like, the sort of ADAF idea, accretion, advection dominated accretion flows. The alternative, which Ms. Beagle and I thought about, was that in fact this energy gets carried off not by radiation but by an MHD wind essentially, and this is our sort of ADIUS representation of what goes on in the disk that are not able to radiate, and these are the ones that are supplied at a low rate are believed not able to radiate. So I'm now going to talk about the extraction of energy from the spin of the hole, and as I said, this is obviously a very quick overview, but just to drive home some basic points that are essential for what I want to say going forward, is that it's described, we believe, by the Kerr metric. There are 2 frames that are sort of interesting for this purpose. One is the frame that is not rotating with respect to infinity, the so-called Boyle-Lindquist frame, or the B frame. And this is the frame in which there are conservation laws and so on. In addition, we can define locally a so-called ZAMO frame, zero angular momentum frame, and this is one in which a physical observer would have to exist close to the black hole, and an observer, as that observer approached the event horizon, would rotate with the angular frequency of the event horizon, just hovering just outside that horizon. The region when the observer must rotate with respect to distant objects by this dragging of inertial frames is called the ergosphere, and I'll return to that in a moment. Now, the means of extracting the spin energy of the hole is, we think, essentially electromagnetic, and the simplest description of this, and again, I'm just like the accretion disk, I'm just going to keep it as simple as possible initially, and that is to describe this electromagnetism as just being force-free. There is no matter, and this is different from the philosophy of magnetohydrodynamics, where there is presumed to be gas and it does have a fluid velocity and a pressure and a density and so on and so forth. This is just simply autonomously electromagnetic, and is just simply force-free, and the force density vanishes. So we ignore inertia altogether. If you then go through all this, then you can define, making these assumptions, a set of axisymmetric flux surfaces in which the magnetic field lies. These have a characteristic angular velocity, these flux surfaces, that's conserved along them. There's a current that flows along these field lines, and we can talk about an interior current, and that is responsible for toroidal magnetic field, as depicted over here. And then also associated with this is a torque given by these formulae here. This is a magnetic torque, and it corresponds to, in the B frame, angular momentum going outwards along these magnetic surfaces. And for the same reasons for a disk, they also carry energy or power along these surfaces too, at this rate omega times the element of torque. And the key thing is, in the Boyle-Lindquist frame, the energy, the power just comes straight out of the black hole. But if you ask what an observer would see in the Zamo frame orbiting just above the horizon, then due to frame transformation, you would see power going into the black hole. So one's general prejudices about black holes are not challenged by this. So this magnetic flux that can extract the power in this way has to be sourced by an external current, and typically the efficiency of extracting the spin energy is about a half. So there is increase in the mass of the hole, and this corresponds to dissipation. But these sorts of black holes are very polite. All of the dissipation happens, they close the curtains so that you can't see all of the dissipation going on. And so this is happening beneath the event horizon, and so you're not seeing it. And what emerges from this is an essentially invisible pointing flux of large-scale electromagnetic field, which will ultimately become the jets that you observe. So one of the ways of building a model for this, and this goes back to the 1970s, is to recognize that these low accretion rates, they cool, and there is an ice that forms, that's supported by the pressure of hot ions, accompanied by much cooler electrons. And this provides a pressure and provides a channel, if you like, a funnel, in which this electromagnetic power can be collimated and make the famous jets. And so this is what one story, this is a cartoon that came from a paper in the 1980s that Martin Rees and Mitch Bakerman and Stel Finney and I wrote. And there have been many simulations, very sophisticated and very impressive, using MHD codes of this this type of configuration. And this is in reality the model that is generally believed, quite possibly quite correctly, to describe the M87 black hole shadow and the orange ring of gas that you see around it. But I'm interested here in exploring an alternative. And just to drive home why I want to do this, let's talk about radiative efficiency. This is all things that are fairly well known. In Sagittarius star, the power is roughly about 10 to 36 ergs per second. The mass supply is 10 to the 21 plus or minus 1 grams per second. And the efficiency, just relative to the mass supply, is 10 to the minus 7. Or so in units of C squared. That's one way of doing this. In the case of M87, then the jet power, we believe, is about 100 or so. There's some argument about this. And that's 100 or so times the observed disk power. If you're going to do this electromagnetically, then the field strength, again, we can make models with different numbers, larger and smaller, but the field strength would, I think, be somewhat like about 100 Gauss. The cooling time of a synchrotron emitting electrons about 1,000 seconds. And if we say an estimate of the electron pressure would be something like the millimeter power times the cooling time divided by the volume of this torus, which is kind of observed, and that would be 10 to the minus 7 or so of this naive magnetic pressure. So again, it looks like there's some sort of problem there. The real fundamental issue is, why are the disks associated with this powerful jet in M87, why it is so inefficient, why do we not see it much, why is it essentially invisible? So what I'm going to propose here, in fact, is that an alternative that's at least worth exploring is that what EHT is looking at is not an iron torus like this, but instead a magnetosphere. So here's a cartoon, and I'll just go through this rather quickly, and then I hope stop and leave time for questions. I'm just going to outline the sort of story, if we like, and without going into the details, some of which, as I say, is very much a work in progress. So what we have here is a black hole. We have this region shown here with dotted lines around it. I call that an ergomagnetosphere. This is a region that is threaded by magnetic field, and it's magnetically dominated, this region. This magnetically dominated region, and it's essentially within this region here, the magnetic field lines, just like a putative observer, have to rotate with a finite angular velocity relative to the distant stars, and some fraction of the angular velocity of the black hole. So the field lines themselves must actually rotate with that angular velocity, and that's the omega that was in the previous slide. So we have this here like this. Then in this sort of geographical, if you like, view, outside of this region is some sort of interface, which I will call a magnetic clutch. And in here, there's more magnetic field. This again is still magnetically dominated. And then further out, there is an accretion disk, because all of this magnetic field must be held in place by some external stress. And the best way to do that is, we know there's an accretion disk in M87 and all these other sources. We know there's gas falling into there. And the claim is that it's this disk, albeit at some remove from the black hole itself, that is confining all of this magnetic. And then we put a rapid spinner in the middle of it, which acts like a sort of imperfect conductor, and that induces an EMF, which drives a Poynting flux off in these two antiparallel jets, in the way shown here. I call this here an ejection disk, as a sort of different Latin construct, if you like, from the accretion disk, because what is actually going on here is that all the gas that is supplied is actually driven away by power that comes from the spin of the black hole and is communicated out here to the ejection disk, and essentially all of the supplied gas at large rate, which can be 5 or 6 orders of magnitude more than appears to be accreting, is blown away from this disk and never makes it to the black hole. So this is an extreme version, if you like, of the adios view, which Spiegelman and I developed. And so I will call this then an ejection disk. And in the middle, the jet itself is powered mainly by the field lines that thread the horizon of the black hole, as depicted here. These field lines that thread the horizon of the black hole, and they make the accretion disk. So if I then try and summarize this, the region, this ergomagnetosphere, I would claim is magnetically dominated, like in a radio pulsar, for example, where the magnetosphere is magnetically dominated. The current that you need of these negligible plasma, so you don't need any gas there. You will, in practice, of course, have some, because magnetic, plasma is very slippery, and there will be a steady flow of gas inwards. The field lines that thread the horizon will travel with some fraction, will orbit with some fraction of the whole angular velocity. Now, there's a real problem, though, that comes up in this picture, is these field lines that I'm showing with my cursor, here, these field lines here that go through the horizon and don't go through the hole, they must rotate and they must carry away power, and they need a source of power. Now, one of the ways in which simulations and others investigations have addressed this is to put in a current sheet here and essentially allow, essentially allow all of these field lines here to thread the horizon of the whole. But I think that it's worth considering an alternative, that they in fact are supplied with energy and angular momentum. And contrary to what happens in the simple model of the magnetosphere, there is a communication of energy and angular momentum, a sort of friction that connects one flux surface to the next, just like in the disk. We believe the magneto-rotational instability connects one radius to the next. So there's a transport of energy and angular momentum, not just along the field lines as in a simple model, but across them too. And it can go all the way out to the accretion, to the ejection disk. And what you're seeing here, in fact, I would say is not a great big thick torus, what the EHT is seeing on this model, but a series of current sheets. I won't go into details about that. So if we look a little bit more about this magnetic clutch, then as I've shown in this red line here, there's a transport of energy and angular momentum, not just along the field lines, but across them. And the source of this friction that carries out angular momentum from here to there, the torque, if you like, is essentially magnetic instability. And this is something that perhaps others have been thinking quite a lot about, don't quite know how this all works out in the end. This is, sort of, as I say, a work in progress. But let's put this as a conjecture, there's a bit more to it than that, that there are instabilities associated by this magnetic shear flow. They grow to nonlinear amplitude, they become essentially turbulent like the MRI, and essentially in this region here, the magnetic angular velocity of the mean field decreases from some fraction of the black hole angular velocity to the Keplerian angular velocity in the accretion disk. So that's there. And now if I just look at the ejection disk, I think I've probably said most of this. It's necessary to retain the magnetic flux. It's necessary to collimate the jet. And as we see, that's actually happening. So you need something out there to do that. And my belief is that it's actually all of this, it's gas that's being driven off by the ejection disk with its magnetic field, that's toroidal magnetic field that's wrapped around it, that's providing that collimation. And it's powered by the spin of the black hole, not by the release point. You get no more than started off with. Now, this energy here, if this is going to work, it must be transported from the black hole to not too high an altitude in the outflow. It's got to be below what's called an infalling surface, which is still essentially in the region that's still essentially in causal contact with the ejection disk. And also, as is sort of conjecture, if you like, this is also the source of the, perhaps in those sources that do have emission lines, of the emission line clouds to it, this ejection gas. So that's the basic story. I'm not going, as I say, I'm not going to belabor in this preamble, if you like, the observations, although I'm keenly interested in them. One of the things that one has to do, as well as understand these instabilities, is trace the ring, is to trace rays and so on in this environment, and that turned out to be rather interesting. There's been a lot of work actually done on this. I must admit, I'm not totally understanding of some of the claims that have been made about caustics and so on, because I did work on this problem once with Kevin Rauch, and I'm not sure the caustics are really so as prominent as is claimed in a typical geometry where you just trace a ray through. You don't think you actually see so much from a caustic, but that's perhaps for another audience. But you certainly do need to know what's along and at the end of those rays to what you actually see. And that, of course, is where the modeling of these flows around black holes, electromagnetic or hydrodynamic, actually come in. And if I just put a quick summary of what I've said, is I've tried to present here an alternative view of the EHT observations, and of course much else besides. It's a magnetosphere, not an iron torus that you're looking at. This has many implications for observations, some of which I know are in the works, as it were. And for the whole electromagnetic spectrum, because it has big implications for the gamma rays as well as for the radio, and also implications for AGN in general. And the future is bright because as I emphasized, we're going to observe these things more using EHT and other ELBI observations, and looking forward to NGVLA. Simulations are in capability are improving impressively, and I'm no longer really heavily involved in this except as a sort of hanger-on. Very impressed by that, but I think there's also time to stand back a little bit and think about some of the alternatives. And even if we end up ruling out the story that I've just tried to tell, I think there's still room to do that. So I'll stop at that point and then go ask for questions.
Wonderful, Roger. Thank you very much. That's a great talk. You had a captivated audience of 300 people. Okay, we have a number of questions to try to go through, and I'll try to relay some of the best ones forward to you. So first up, does this model make a specific prediction on the polarization properties of the EHT image, for example, for the future?
Yes, I think so. But I don't know what, because there are many. I emphasized that what I think you're looking, the emitting elements, which are intrinsically radiatively inefficient, are essentially current sheets. I think there is some volumetric emission, but it's essentially these surfaces that are large-scale surfaces in the ergomagnetosphere. And where you put them, determines the polarization. The one thing that I would say is that the polarization ought to be high. I'm not so sure about what one actually sees, because I know I've explored 4 or 5 different, current sheet geometries, which will give you different directions, but it's generally high. And if you make naive models of the torus, then that's a lot of Faraday rotation associated with it. And although I think it's possible, and I think there are many models that have been produced, which I believe, I gather, predict polarization, but I would have thought generically the polarization ought to be low in M87. So I would say yes, high, but I'll hedge my bets on the direction, because I think there are many different geometries one can explore for the current sheets.
Okay, excellent. This is kind of almost a follow-up question. Are there any other observational differences between the iron torus model and the magnetospheric model?
Well, I think there will be, yes. And I mean, we are, with more baselines and going to 0.8 millimeters and so on, one is looking at improved resolution. And I think there are going to be differences. For me, the challenge is with the iron torus model, which, I'd love that to be right, because it was, in some sense it's a simple idea, but, making a really good story for why it is so radiatively inefficient and why you only get emission from a very small fraction. It has to be coming from a very small fraction of the volume if the fields are anything like 100 Gauss. And, there are ways out which have been explored of having saying the jet is much lower power at the moment. It's in a very low state. And so we have less magnetic field and so on. I think it's still very hard to make it radiatively inefficient. And I think, some of the progress will come from simulations. I mean, we've got a plasma here we want to keep protons and electrons at different Maxwellian temperatures, when all of the instabilities known to man should be there, and trans-relativistic, transonic, trans-Alfvénic, and so on. So this ought to be a pretty virulent environment. So I think if you can demonstrate that can really happen at the microphysical level, I think that's the way forward. But there are going to be observational comparisons with simulations, and that how adaptable the simulations are going to be, I don't know.
Okay, and aside from the EHT scale, which will improve and will also prove that you'll have dynamic observations to help as well. On slightly larger scales, we're going to see a lot of improved performance, including in GVLA. Are there predictions that extend further out from just the immediate environment of the black hole?
Yeah, yeah. I think one of the inferences that I drew before the EHT observations, I think other people did too, was just looking at the NGC 1275 and so on, 384 and so on, is these limb-brightened image jets that look like they're an interaction. So it looks like there's something, a jet has a fairly hard surface as it propagates away, and it's interacting with something that is also collimating and confining it. So I think understanding observationally the nature of the outflow from the disk, and I claim it's a somewhat remote ejection disk. I think, the Iron Torus interpretation would say this is a wind that comes from the surface of the torus. And so, in some sense, there's no magnetic clutch. There really is a gas all the way down to very close to the horizon of the black hole. I think that's observationally explorable using VLBI on different sources where you're not resolving the black hole, but you are making comparable images of these different types of AGM.
Excellent, thank you. Another question, I think you tried to clarify the distinction between the accretion disk and the ejection disk, but there's still a little bit of confusion in that regard. Could you say again where material is inflowing and where it's outflowing in your model?
Yes. Okay. Basically, I think in sources, take the galactic center, for example. I think the sort of traditional Bondi accretion rate, I'm not sure how relevant this is about 10 to the minus 6 solar masses a year. The mass supply rate from stars and so on is generally estimated to be about 10 to the minus 4 solar masses a year, and yet it is fabulously dim and essentially invisible, and yet we know there's a black hole there. So the claim is that essentially all of that gas, 10 to the minus 4 or 10 to the minus 6 solar masses a year, is blown away, and no more than 10 to the minus 9 solar masses black hole makes it down to the event horizon. And so what you have is a flow of gas that is supplied at large radius. It might be the molecular torus at 1.7 parsecs or so on, and it flows inwards, but all the way as it flows inwards, it's being more and more of it is driven out, and it needs energy to do this. It essentially has zero energy at infinity, and the ejection disk has to be powered. And the claim is it's the spin energy of the black hole that's communicated to the inner edge of the ejection disk, propagated outwards through the ejection disk, and drives away essentially all of the gas that is supplied. So essentially nothing makes it down into the horizon. That's the story. Now you can find sort of intermediate states between that and the traditional accretion disk, but that's the sort of, if you like, fairly extreme view that I'm pushing here.
Thanks, Roger. Next question is, how would the energy extraction depend on the co-rotation and counter-rotation between the disk and the black hole?
Oh, yes. Again, that's interesting. I think there have been several papers that have talked about, well, let's have an accretion disk around a counter-rotating black hole. The innermost stable circular orbit is much further out, up to 9M and so on. So that would be different. I think I have to say I've been mainly thinking about M87, where we kind of know that the spin of the black hole is in the same sense as the spin of the gas at large radius. So it's essentially a co-rotating structure. Have thought a little bit about that there. The magnetosphere is rather different, and it's rather interesting, but I haven't really explained what happens in the co-rotating case. So I just say it is an interesting question, but at the moment I'm more fixated on the co-rotating case.
That's reasonable, Roger. Yeah. Next question. If the mass supply efficiency is so low, how can we explain the formation of supermassive black holes?
Oh, well, I mean, it could be, M87 just grew in some enormous gravitational collapse in the very, very early universe. but I think most people believe that it grew. And if we look, there's an argument goes back to Andres Salton long ago that says that if we just look at the integrated background light from quasars, which are typically most active at a redshift of about 2 or so, and we just ask how much energy density is there associated with that, then we find we do need high radiative efficiency. So all of these bright quasars, which are observed and catalogued by 4 million Sloan quasars and so on, they are active at, as I say, at redshift of 2 when they were being supplied with gas at a prodigious rate. So in the final build-up, say, of M87, as I think I said, this would have been brighter than Vega on the sky. You'd be navigating by it. So that would have been prodigious. The story I'm telling here is really what's appropriate when the mass supply is very much lower than those times when the gas really does make it down to the horizon and does grow the black hole. So I would say the mass and the spin are built up during this period, and the spin that we have sitting in M87 now can keep the Virgo cluster warm and toasty for 10 to the 14 years. So there's plenty of energy there now.
Okay, the questions are coming thick and fast here. Roger, what is meant by magnetically dominated? How strong should the magnetic field be relative to what, and relative to what to be called magnetically dominated?
Well, plasma physicists are fond of a quantity called beta, which is the ratio of the gas pressure to the magnetic pressure. And what I'm saying is that is very small. How small? If you ask, what's the minimum gas you need to carry the currents, then it's like 10 to the minus 11, but that's ridiculous. I mean, this gas is going to get in there. I would say, 10 to the minus 1, 2, or 3 or something, it justifies calling this a magnetosphere. Just like there's gas within the Earth's magnetosphere, there's gas within a pulsar magnetosphere, and so on. It isn't absent, it's just not dominating the dynamics.
Okay, next up, how different is your idea compared to the Yugospheric wind model proposed by Punsley and Cornetti in 1990?
There is some similarity to that, yes. There's also some difference, but it's more sort of, if you like, at the technical level. I mean, I think actually there were variations on that too, but I think there is the idea is that you've got to have a source of energy. You've got to have a source of power that lies on the end of the field lines that thread the equatorial plane of the black hole between the horizon and the disk. And you've got to have some source of power, and my contention is that is actually transported across the field lines rather than coming from the equatorial plane. But there are some similarities, I agree.
Okay, just a couple more now. Could black holes attract each other magnetically?
Can black holes attract each other magnetically? Okay, let me give an oblique answer to that. In the case of a single black hole, it is absolutely necessary that the magnetic field be supported by currents outside the horizon that hold that magnetic flux in place. That's the story that has to be told. Now, many people on this call will be aware that as an extension of the Kerr metric for a spinning black hole is Kerr-Newman that has a charge as well. And that's a splendid solution of the Einstein-Maxwell equations. However, the charges that you would have there to be gravitationally significant would immediately discharge. And so it is, because of QED, really thought not to be a tenable way of having a magnetic field. So if you want to have a binary black hole interact electromagnetically, then you must have a ring of gas around it. And so, you know, people have looked for LIGO binary black hole mergers. They've looked for electromagnetic signals and have not found any as yet. And I think it is generally thought that a less unpromising source of these might be, when they're eventually seen, is massive black holes, perhaps in black hole binaries merging in galactic nuclei, because there you might have a large sort of circumbinary disk that can trap magnetic fields, and you've got this kind of egg beater there. You've got these two spinning black holes, and this is like a classic. This is like a classic binary mechanism. In fact, I did think about this with Willis once, actually a long time ago, and then Willis did a better job on this. And the idea was that if you had, say, a binary black hole, it could act like a dynamo in principle, and it could have, you know, two spins that would reinforce each other and build up make an electromagnetic bomb. And I sort of did think about it a little bit. I was rather skeptical, but Willis actually did do some calculations, and sadly they confirmed in a subtle way, very, very important, my original skepticism that this could happen. So, but you could do something a little bit richer if you had a large circumbinary ring there that was trapping magnetic flux, and you had these two orbiting spinning black holes inside it. That could be rather interesting electromagnetically and make a rather fine display just before merger. But that's rather speculative and probably much more likely to happen in a galactic nucleus than in a whatever the environment is of a binary black hole. There have been suggestions, actually your colleagues at Caltech have been suggesting this, that these binary black holes could happen in accretion disks in galactic nuclei. That's an interesting idea, and that's perhaps one way in which you might think more about the answer to that very good question.
Yes, that's right. Okay, could you elaborate on what is meant by parallel polarization? Is the polarization high because of low rotation, or is it because of tenuous plasma?
Oh, low rotation. I'm not, I mean, it could be there's a lot of plasma there, but I'm envisaging that there probably isn't an awful lot. And so the amount of proper rotation of the plane of polarization going through the gas around can be made rather small, is typically rather small. And I think that is a constraint on models of ion tori.
Okay, does the central object have to be a black hole? Does it work for a neutron star? This magnetic clutch model?
Ah, well, not only does it work, it's been invoked. There, of course, the big difference is it's the currents in the star itself, which is an excellent conductor, that trap the magnetic field and cause the field lines to rotate with the spin of the star. And then there are models of magnetized neutron stars that have essentially an Alfvén radius, where some magnetic field, accreting gas gets attached to the field lines, and then generally is thought to flow down towards the magnetic poles of the magnetosphere and hit the surface and then radiate X-rays. And then also there will be, of course, dynamical interaction with the disk itself, and you can have spin up and spin down of the neutron star, which you can measure using facilities like now it's done facilities like NICER and so on. So yes, so not only is this possible, it's been exhaustively discussed since the 70s. This sort of general possibility. The thing that's sort of novel, if you like, here is that to do this in a poorer conductor, where the resistance is typically about 100 ohms or so, which is the black hole horizon, and that really requires you to hold the field in place with the gas around it rather than tie it to the black hole.
Fantastic, Roger. There are still questions streaming in, but I think we better stop there, or you'll be here for the rest of the day. Thank you so much for a wonderful presentation and your patience in answering so many questions. Thanks to you all for joining, and I'll remind you that the series resumes again next week. Thank you all.
Thanks from me too.